this thing called the scikit learn library, which was something I had a lot of experience in using this summer in my internship at Tufts University in their data science program. And yeah, let's get started. So, one thing that's kind of important that we discuss before we get into the weeds of the scikit-learn library is what is machine learning actually? So, in order to uncover what machine learning actually is, we have to go back to its origins, which is in 1959, which is where you see the guy in the upper right. That guy's name is Arthur Samuel. He was a computer gaming and artificial intelligence scientist, essentially. And he created what is known as the first successful self-learning program. And it was a checkers playing program that could check if somebody had won the game, essentially. And yeah, so that's kind of the roots of where machine learning started, which is all the way back in 1959. A little bit about Arthur Samuels. He was born in like 1901 in the middle of Nowhereville, Kansas. And yeah, he became one of the pioneers for something very like technologically like advanced for that time. So a little bit of Monday inspiration for y'all. But yeah, as far as the layman's term definition for machine learning, what I ended up doing was I borrowed a definition from an intro to machine learning course from MIT, and they define machine learning as the capability of a machine to imitate intelligent human behavior. And by intelligent human behavior, that just means the way we think and we kind of classify and identify things. So just for today's DBM, if you're gonna want to like go along with the code at the end when I show the example, I'll also post the code later, like at another time. But if you want to code it with me while I show you kind of the activity, the libraries you're going to need are the pandas library, the scikit library, Quandl, which is where we're going to get our data sets from. We're going to be using doc data sets to predict the end of the day, like the closing price of a stock. And you're also going to need the math library. So, kind of reaching back to the definition that I shared at the beginning of the presentation about how machine learning is essentially just how well you can program something to imitate human intelligence. Uh, there's three basic types of machine learning: it's supervised learning, unsupervised learning, and reinforcement learning. And for me, the easiest way to understand these three types of learning models or three types of learning categories is think about it in terms of like when you were a baby. When you were a baby, like you didn't know anything. Your brain is a completely like blank slate. There's three types of learning you can get when you're a child, and it's supervised learning, which is when you see an orange and your parents are like, "Yeah, that's an orange," right? So now when you see things that look similar to an orange, your brain says, "Oh, that is probably an orange," and you can classify oranges pretty well now, probably, hopefully. So unsupervised learning is kind of if you don't have that parent figure to tell you this is what this is, you have to kind of deduce and detect patterns with your own senses. For example, your vision, your touch, your hearing, your taste, your smell. You use those things and you detect patterns and you group things together. For example, you can group things that are red together and things that are blue together. You can group things that smell bad and things that don't smell bad. Right? So that's kind of unsupervised learning is you don't have these labels that a supervisor is providing you. You are completely free to sort and classify as you will. You're just searching for patterns. Reinforcement learning is actually a really interesting one. Reinforcement learning puts emphasis on rewarding positive decision making and punishing negative decision making. So with a model that uses reinforcement learning, it would be something along the lines of you would train a model, right? And then you would present it with some tests. And if it classifies it correctly, the model would be kind of like positively impacted. If it's negatively guessing these or predicting these pieces of data, giving the wrong labels, it'll like be negative. So in this figure to the right, I've borrowed this from the course that they actually had us take at Tufts this summer. So as you can see, this is a example of supervised learning method, well, model. And as you can see, the blue box, which encompasses everything, is pretty much training. So you give it a classification task, you provide it with labels that are paired up with data, and this will establish your line of fit. And then you can get a performance measure from feeding in testing data and having your model label it, right? And based on the total amount of data that you were trying to test and how many pieces of data were correctly classified, you'll get a performance measure that is usually less than one, but higher than zero. So it's a fraction of some sort, and it's pretty much telling you which fraction of total data you classify correctly with your model. So for today's GBM, we're going to mainly be talking about linear regression because that's what our example is going to get into. But we'll also conclude by talking about like a lot of different other types of machine learning models that the scikit-learn library does offer in Python. And a really important part of that is before this summer and before I started getting really involved with machine learning and these models and just Python in general, I never viewed machine learning as like a tool that everybody has in their back pocket. But nowadays, like it was different when Arthur Samuels was around and you had to like go to another state to get access to a computer. Now in this era, you can literally take out your laptop and rent out a high performance computing cluster for like $5 for 24 hours and do some serious high level classification tasks. So this is really a tool that everybody has access to, no matter who you are. And I think it's important that we recognize that and take advantage. So, for example, linear regression, it takes in a stream of continuous data and it creates a line of best fit. So if you look at the figure to the right, like the bottom right, you can see a line that's formed with the slope intercept form y equals a plus bx and then plus some degree of error. This is the basis for linear regression. You get a bunch of points or the actual data, and a regression line is fit that minimizes like the total distance of points to that regression line. So it uses some minimization logic to do that. Now, this gets into like residuals, and which is error, like from the regression line or the line of best fit. It will like measure the total distance away from the real points. I'm not going to get into that too deeply in this presentation, but if you have any questions about that, you can ask me afterwards. Essentially, linear regression is you taking that slope intercept form, and your regression is learning the slope and the intercept for this line. Now, another important part of machine learning is training and testing a classifier or a model. So not to read up the slide, but like when you're creating a classifier with a machine learning model, you're going to have to train your model, right? If you don't train your model, there's no baseline to compare anything you want to classify with, right? So training is essential. And when you train your model to build that kind of baseline classification or baseline slope or line or sigmoid curve, if you're doing logistic regression, you're pretty much taking a pool of data that hopefully you've shuffled with some degree of cross-validation to make your study or whatever you're doing a little more concrete, a little more robust of a study. You would then test it with some also cross-validated data. That's literally you just shovel your data. And yeah, you can run this testing set, which is just the X data, through your trained classifier, and it'll yield you labels or outputs that it can deduce from the data you trained it with. So some of the like applications for machine learning and just even the scikit-learn library that I saw this summer, and I saw like in universities across the country, and honestly, I can just infer that it's going on across the world, is people are using these very, very basic, like rudimentary scikit-learn libraries to train and address large scale classification problems that have large implications on like society and use like I think the correct classification for it is big data. So they're using boatloads of data, um, and it's actually honestly an amazing field to get into. If you're into math and like if you're into like heavy theory and math, machine learning is for you because there's a lot of math and data science. But some of the modern classification problems that I saw being addressed, like over the course of this summer, my research worked on brain-computer interfaces, where we were training a model to take data that was collected from this device that measured functional near-infrared data, and you would wear it like the cap this person's wearing in the picture, and it would take like like deoxy and oxyhemoglobin sample, like it would monitor deoxy and oxyhemoglobin in your brain, and we would try to use that to classify how hard a person is working. We got like upwards of 70% accuracy, which was really good for that data set that we were working with. And we were using linear support vector machines, which is another type of model that's available in the scikit-learn library. So I know something that my brother does, Josh, the vice president, his research revolves around like validating like what news is like um not fake essentially. So there's big applications to this in social media, autonomous vehicles, so like Google self-driving cars. Google also has a lot to play in these last three because even cybersecurity and fraud, Google has part to play in malicious users like detection and intrusion detection, as well as virtual assistant AI like the Google Home, Siri, Cortana, Alexa. Yeah, but oh my gosh, my Alexa just went off in the background. No, I'm not talking to you. But yeah. So let me show a quick example in Python. If I haven't closed it, which I hopefully haven't. All right, can y'all see my screen? The code?
Very
Hope.
good.
All right, awesome.
Yes.
All right, so I sent a little, well, I didn't send a little, but I put a little screenshot of all the libraries you would have to include for this example that we're doing today. So the example that we're doing today is using what I was explaining earlier, Quandle. Uh, Here, I'll even show you the website. Um, where is the website? I think it's in here. Here it is. Yep. So Quandle is no longer called Quandle. It's called data.nasdaq.com. And essentially, you can go and get all different types of stock data sets off of this website for free. And there's like no limit. Like the sky's the limit to to how many data sets you can pull. It's completely open source. Um, if if you want to adventure deeper into this, I highly encourage it. The example that we're doing today is we're taking, well, I took the Microsoft Corporation stock prices, and we're predicting the closing price of the stock. So what we do, well, what how we kind of set this up is we're going to use quandle.get, which is a function that essentially, if we pull this identifier, here, I'll show you even how I did it. You go here, you click on Python libraries, and it'll give you an identifier that you copy and paste, and you can put it right into your code and save it to a variable. That's what I do to start off. I start a data frame and I say it'll be from Quandle, and I'll get the Microsoft. Um, I think that stands for end of day. So the Microsoft like end of day data set. So what I do is, of course, like I print out this data frame just so I can see kind of what type of variables I'm working with or what type of labels, well, not labels, features I'm looking with in my data set. And this is actually a really important part of machine learning is seeing if you can visually or graphically see a trend in your data. Because before you train like your models on like 74 different features that you're not sure if all of these features are even going to be like meaningful in a classification like problem, you might want to take a look at what variables you're dealing with and kind of visually and graphically pick the most significant ones towards your classification. So, for example, we didn't use high and low, right? But in the following lines, you can see that we did use like high and low to create a new category of feature, right? So I know nothing about stocks, so I got this math just straight directly from the internet, but it helped classify the end of the day like closing price of these stocks heavily, right? So even like this goes to say you don't even really have to know about what you're trying to classify if you have like a deep enough like passion to for a classification problem. You can literally just go on the internet, get some math if your data set has like the variables kind of to for you to get your new variable or whatever would help you more like accurately classify something, you can go ahead and transform your data set essentially. So we do that twice here, and then we reform and restructure our data set by we only keep adjacent or adjusted close and adjusted volume, and we add our two new features to our data frame. Now, we have one label, which we call our forecast column. So we set our label as our forecast column, and we have three features that we'll use to try and identify this closing cost, right? So, and that's the high-low percentage, the percentage change, and the adjusted volume of the stocks. So one thing that you always have to watch out for when you're dealing with scikit is it really doesn't like null values. So wherever you have a null value, just make sure you go ahead and you use. It has this awesome function called the or method called the fill NA. It fills your nulls, and you can pick which value to fill it with. It's just standard to fill it with like a really high negative number, or really, I guess, in reference to like where the origin is, it's a really low negative number, and you're just swapping it in place. So you go down and you can see here that we create a new DF with a tag label, and we assign it to our forecast column, which is what we're trying to classify. The closing, like the adjusted closing price of the stock. So this is where we actually train and test our data. So for example, for X, what we'll do is we'll take our data frame and all we're doing is we're dropping the label column because this is what we're trying to identify. So our labels will have to be solely our Y, right? And we have to separate them from our X. This is important because when you train, you use X and Y, but when you test, you don't use Y. So afterwards, we do this thing called pre-processing. Now, pre-processing is really important when you're dealing with these machine learning models because you can reduce the time it takes for your model to run by doing this thing called pre-processing, which essentially puts all of your features as a number between 1 and -1. So instead of like having numbers from like, as you can see in adjusted volume, from like I don't even know how much this is. This is like in the I think it's in the millions. It's 154 million. Instead of having a number like that, you would have a number between -1 and 1. And it makes it a lot easier to classify on your computer. So if you're dealing with large data, it's very important that you do pre-processing. If you're dealing with smaller data sets, maybe it's not as important, but it's still encouraged that you always pre-process your data. What we do here is we use the train test split. to split our data into training data, testing data, training labels, and testing labels. And after this, we can say our classifiers of type linear regression. This is straight out of the learn scikit learn library. There's over 200 different types of classifiers and models that you can train and utilize in that library. And that's why I think it's like one of the most like robust libraries out right now for machine learning. I really enjoy using it. In this loop, we're kind of just showing the different types of models, for example, that you can use. Um, so yeah, so this will select the classifier. What the what the fit function does is you give it X train and Y train. So you give it your X train data and its correct labels for that, and it'll essentially build your fit. And then your confidence is just your score, and your score is what I explained at the beginning. It's the total number you've tested. Well, it's not the total number you've tested, but it then takes um, the data that you're testing and it pairs it with the correct labels for that data, and it compares it to how well it would fit. Well, how well not that it would fit, but it would classify X test. So that a way you can do this without score is there's a function called predict. So predict would be clf.predict, and you would only include the X. You wouldn't include the Y. So the thing that score does is it lets you know your accuracy. Prediction will yield you a matrix of predictions or labels for each of the X test inputs. So without further ado, I'll just run this again. You can see the output on the bottom from earlier. It shouldn't change. And I'll kind of explain these values to you. So linear, that correlates with linear regression. It looks like we have a 97.9% accuracy in predicting the end of day stock prices for Microsoft with this model. So this polynomial regression, not as successful because polynomial regression has an issue with overfitting, because what polynomial does is like it has a bunch of different curves, right? So it'll try to fit the data that you train it with really, really well, which can make it really inaccurate when you have testing data that is not super closely similar to what you've trained with. That's why you will see like a dip in accuracy here. This is a random forest. Random forest is a really, it's a lot more complex than linear and polynomial regression. It's more so like drawing like boundaries around like certain areas and saying like this area classifies this area we can classify as this. This also had a very high performance of 95%. And the sigmoid function is what we call logistic regression. And as you can see, logistic regression is not very good at classifying stocks, but this is a little bit of higher level stuff. But logistic regression models have a bad rep for outlier data. So in stocks, stocks go up, stocks go down, stocks tank, stocks skyrocket. Like there's a lot of times there's no rhyme to the reason. So something that's really sensitive to outliers would be a very poor classifier for this type of classification problem. But yeah, this code is going to be sent out later. I'm going to post it on the IEEE, well, on the Discord. In the weekly email, I'll probably send it out as well, along with the presentation. If you have any questions about the scikit learn library, I'm here to answer your questions. If you're ever using it for research, if you're using it for anything, I have a pretty good like handle on it after like being like thrown into the ocean kind of machine learning this summer with no with no life raft. Just had to kind of learn how to swim. But yeah, so for the models included in this library, there's support vector machines, random forest, which we mentioned in our example. You can use neural nets. You can do clustering. You can use mixture models, manifold learning. There's tons of other models that I didn't list on this slide, but like I said, there's around 200 models in the most up-to-date scikit-learn library. Um, the sky's actually the limit. Like this is such an amazing tool. I really do encourage anybody who's interested in using machine learning and like anything they do involving data. I definitely encourage you to do it. Like even if it's like you generate data for maybe like a class or a project or something, um, and you're interested in seeing how well your data that you collected can be classified and trained, I would definitely like run it through machine learning. I think it's a really cool kind of tool to have. Um, but as for next week, we have a really awesome GBM coming up about building a PC, and that's with my roommate and the laboratory manager, Xavier Smith. I'm not sure if he's here right now, but that's one to look out for next week on Monday. And aside from that, I'm open to any questions. Like I said, this wasn't going to take like the whole hour. It took kind of exactly around 30 minutes. But if there's any questions, I'm here to answer them. But if not, uh, no. Yeah, what's up tomorrow? Yeah. How do you save the model? That is a really good question. You see, I never saved my models. What I did do was I would export data to Excel spreadsheets, right? So the performance of the model I would log, right? But after I trained the model, I wouldn't save it. So there's probably ways where you can save like the math that because when you train a model, you're establishing a fit for supervised learning, right? So there is definitely a way to like kind of save the fit that you've established. I do not know specifically how to do that, but scikit-learn library is very well documented. So there's thousands of functions, thousands of methods. Uh, there's bound to be something in there to save it. All right. So if there's no more questions, I'm gonna drop my email in the chat. You want to email me any of your questions after